So Gabriele, he got his PhD in physics and astrophysics at the University of Insubria, where he specialized in quantum technologies and simulation of complex quantum systems. During his doctoral studies, he was also visiting as a PhD student at the Queen University in Belfast. Today, he is a postdoc at the Institute for Cross-Disciplinary Physics and Complex Systems in Palma de Mallorca, and his research focuses mainly on open quantum system, quantum thermodynamics, and monitored quantum systems. The title today is Continuous Monitoring as a Resource for Work Extraction in Open Quantum Batteries. Gabriele, the stage is yours.
Okay, good afternoon, everyone, and thank you for being here, and thanks, Federico, for the introduction and the kind invitation. So, let me start with a very brief outline of my talk. So I will start with a very general introduction about quantum technologies, and then I will move to the concept, the main concept of this talk, which is quantum batteries, and also daemonic ergotropy, which is a sort of information-fueled quantum work extraction protocol. And finally, in the end, I will show some results I've obtained in this context. So, let me start. Last year, in 2025, quantum mechanics celebrated its centenary. So 100 years have passed since the early formulation of the theory, and it's quite striking to see how much our perspective on quantum physics has changed during the last century. In fact, UNESCO declared 2025 the International Year of Quantum Science and Technology, and testifying how central our quantum technologies have become nowadays. It was not always like that, since for a long time, quantum mechanics was regarded as only as a fundamental theory of nature, extremely successful, of course, but also very far from any direct technological exploitation. And a famous example is this statement by Erwin Schrödinger, who in 1952 said that we never experiment with just one atom any more than we can raise ichthyosauria in the zoo. So today this sounds almost ironic, since we can manipulate single atoms, single ions, single photons, but also superconductive circuit and so on. And this change of perspective is what essentially what we call now second quantum revolution. So the idea that the most peculiar features of quantum mechanics are not only conceptual difficulties, but also possible resources. So a symbolic turning point, at least for the point of view of theoretical physics, is this statement from Richard Feynman, who in 1981 said basically that since nature is classical, if we want to make a simulation of nature, we should do it using a quantum system. And from that point, quantum information science developed very rapidly. First with theoretical breakthroughs such as quantum algorithms and quantum communication, quantum cryptography, and later also with experimental demonstration. And today, quantum technologies ranges from quantum computing, quantum sensing and metrology, and quantum communication. In the last few years also, quantum thermodynamics joined the party. So that's an however, since as Feynman emphasized in his quote, dealing with quantum system is not so easy, and one of the main reasons is that any realistic quantum system is never perfectly isolated from the external environment. So since we want to measure them, we want to be able to extract useful information from quantum systems, basically they are always in some way or another coupled to an external environment, and this results in non-unitary evolution. This results on decoherence and the loss of the nice quantum feature we would like to exploit. And usually, the standard way to describe a quantum system is the following. We make a bunch of approximation, such as weak coupling and Markovian approximation, and we are able to derive a master equation that describes the evolution of the open quantum system. So usually we have the quantum system of interest is described by an Hamiltonian HS. The environment Hamiltonian is described by another Hamiltonian HB, and then there's some interaction, but we trace out the environmental evolution, and we obtain a master equation for the evolution of the quantum system, which is this one, and it is known as usually as Lindblad master equation or Gorini-Kosakowski-Sudarshan-Lindblad master equation. And this is basically made of two parts. The first part describes the unitary evolution of the system, which is governed by the Hamiltonian, of course. And the second part describes the effect of the environment on the system using this CK operator that are known as that are system operators, and they are known as jump operators or coupling operators, or so on. So we have this kind of scenario, and so let me go to quantum batteries. And so what is a battery? A battery is simply a device that is able to store energy and release it upon request. So for example, a DEM is a nice example of battery. And in the last few years, researchers inspired by quantum science have been starting to ask how batteries works at the quantum level and what sets them apart from classical batteries. And so, we describe a quantum battery as a quantum system that can be promoted from its ground state to an excited state via interaction with a charger. And usually we have this kind of Hamiltonian. We have the Hamiltonian of the battery HB, the Hamiltonian of the charger, which can be another quantum system, and we have an interaction that can be switched on and off upon request. And so why is it interesting to study quantum batteries? Well, of course, for fundamental reasons, to study what are the limits of work extraction in quantum systems, but also for technological reasons, since already a theoretical quantum advantage has been proven in the charging of quantum batteries due to entanglement. So how can we characterize the quantum battery performance? Well, we can, of course, look at the energy, the stored energy, which is basically the mean value of the Hamiltonian of the battery. We can look at this charging power, but most importantly, we can look at the ergotropy, which is a novel figure of merits, let's say. That is basically the amount of work that can be extracted from a given quantum battery through unitary operation. So we have that the energy of the battery can be divided into contribution. The first one, which is ergotropy, can be extracted unitarily. The second one, which is the passive energy of the battery, can only be extracted and dissipated through it, basically. And so how can we calculate the ergotropy from a given quantum state and a given a given Hamiltonian? Well, we have that if we describe the Hamiltonian in its spectral decomposition, and also we describe the state in its spectral decomposition, if the eigenvalues of the state are ordered in decreasing order and the eigenvalues of the Hamiltonian are ordered in increasing order, simply the best possible unitary that extract the maximum amount of work is the one that reorder the population from the greater to the lowest. Basically, the ground state must be in the must have the greater population, and this is due simply because the trace operation, so the unitary operation preserve the trace. So this is the reason. So we have a way to calculate the ergotropy, and the ergotropy has a nice property. It's non-negative and bounded. It is zero if and only if the state is passive, and for pure states is equal to the energy, and it has a convex property. It's important. And so experimentally, what can we do? Well, in the last few years, there have been many experimental implementation of quantum batteries, for example, in optical microcavities with molecules, with fluorescent molecules, but also in nuclear spin systems, in quantum computers, trapped ion, and so on. But as you can see from this table, the thing is that usually the energy density of a quantum battery is really low, and is much lower than the energy density of a classical battery. So how can we deal with this? Well, basically, the thing is that we shouldn't expect that quantum batteries will be used on cars or in our everyday life, but quantum batteries are meant to be used inside the quantum technologies as a source of coherent energy. So that's we shouldn't be aware or scared by this very low amount of energy that we can extract from quantum batteries. So, as I said before, quantum batteries are affected by noise. So noise can degrade the performance of a quantum battery. So how can we deal with the noise in this scenario? And the answer is we can maybe monitor the environment and use this information in order to counteract the effect of decoherence and noise. So let me go back. Let me do let me go back to classical physics and to the Maxwell demon. Basically, in this picture, I show a formulation of the Maxwell demon paradox known as Lizard engine. So we have a single particle box placed in a single particle gas placed in a box at a certain temperature. A partition is inserted in the box, divided into two regions, and the demon, being able to measure the particle location, is able to determine where to put his pulley with his weight in this case, and by connecting the pulley to the right partition and by letting the gas isothermally expand, he is able to extract work that is kBt log 2, seemingly violating the second principle of thermodynamics, since it is able to extract energy from a single heat reservoir. This is not, of course, the case, since we know the Landauer principle, but this teaches us an important lesson that information about the system can be converted somehow into work, and this could be the case of also in quantum system. So how it works in quantum system? Well, we model the environment as a stream of a collisional model of a stream of uncorrelated inputs that interact with the system, and that usually they get discarded. But in this case, we monitor this stream of ancillas, and we use this information in order to construct conditional dynamics. So we can define the so-called quantum trajectories that are quantum state that are associated to certain outcome of measurement. And in general, we have that the state of the system is given by the average over these states, these quantum trajectories, over the average of these quantum trajectories, basically. And this is usually called an unraveling of the unconditional dynamics of the quantum system. And in this scenario, we can derive, we can have many different types of detections or schemes, and we can also derive the master equation from the evolution of the system that depends on the types of detection we perform. So, for example, we can perform photo detection, so we can measure quantum jumps in the environment. So basically, photons that exit the environment, and we can derive this master equation, which has random term that is a Poissonian increment. And also we can monitor the environment via homodynamic detection, and we can derive another master equation, which has this random term, which is a Wiener increment, a Wiener process term. And so the thing is that, on average, the dynamics gives back the unconditional dynamics. But if we, let's say, we exploit the measurement outcomes for each quantum trajectory to maximize the work extraction, so we perform this average, basically, we calculate the ergotropy of each quantum trajectories, and we define the so-called daemonic ergotropy, which is the averages over the quantum trajectories of this quantity. It's easy to show that since the ergotropy is a convex quantity, the daemonic ergotropy is lower bounded by the unconditional ergotropy and upper bounded by the energy. So in principle, by exploiting the measurement, we can extract more work that we could extract with the unconditional dynamics. So recalling the Maxwell demon, information about the system, and in this case about the environment, can be converted into work. And now I show my results regarding these things. So the results are in this paper, which is now under revision. And let me thank also my collaborators, Marco Genoni from Unimi, Dario Ferraro from Unige, and my PhD supervisor, Giuliano Benenti. And so what is the idea now? So it's the key mechanism is that usually also dissipation degrades the quantum battery performance, but also usually battery and charger entanglement reduces the local extractable work. So the idea is in this case, we can exploit the dissipation in our in order to counter-react the effect of the entanglement between battery and charger, in a sense that will be clear later. And I will show this, basically, I will show this in three different models, and I will show that continuous management and dissipation can even outperform the ideal lossless case, since the dissipation and the continuous measurement weaken the battery charger entanglement, which is not good for the quantum battery performance. So let me start with the first example. The first example is simply a two-qubit system. So we have one spin that is the battery, one spin that is the charger, and that interacts with this interaction, this XX interaction, and we initialize the state of the system in this superposition, which is generally entangled for p different than 1 and 0, which is not a good choice actually, but it serves the purpose. And as we can see from the figure, that is for p equal to 6, and on the left I show the ergotropy as a function of the charging time, and on the right I show the purity of the state as a function of charging time. And as you can see, the green line is the ergotropy without dissipation, And then we introduce dissipation, which is the yellow line. And if we turn on the continuous monitoring, which is the orange line, as you can see, we can not only recover the ideal lossless ergotropy, but even surpass the ideal lossless ergotropy. And this is because actually by introducing dissipation and continuous monitoring, we are purifying the system state. And this is not only a toy model, but it can happen also in a more, it can happen dynamically in a more experimentally motivated model. And here I show another example of this phenomena with two spins that interact now via optical cavity. So now the interaction is mediated by the cavity mode A. And now I start the initial state with the battery state in the ground state and the charger state in the excited state. And the battery is in the zero photon Fock state. And as we can see from this figure, we have the same behavior as before. When we consider detection and dissipation, we are able to outperform the ideal lossless ergotropy peak. And again, we show this that the purity is you have a purification of the battery state, and so reduction of the entanglement between the battery and the charger, basically. And this is shown better in this plot, since in this plot I show the ergotropy, the daemonic ergotropy over this Bayer ergotropy, which is the ergotropy, the dissipation-less ergotropy, as a function of this parameter, which is the entanglement loss. And as we can see from this figure, there's a nice linear correlation, at least in the first for low value of entanglement loss, between the ergotropy gain and the entanglement loss. When we increase too much the dissipation, of course, we lose too much energy, and this phenomenon is get worse, of course, because you are losing too much energy into the environment. And again, we show this phenomenon also in another model, which is also more experimentally motivated, which is the Dicke quantum battery, which is one of the most famous example of quantum battery, and it describes basically fluorescent molecules in microcavities. And so it consists in n interacting two-level quantum system coupled to a single mode of electromagnetic field in a cavity. So this is the Miltonian of the system. And the state is initially, the spins are initially in the ground state. And in this case, the charger is the cavity, which is in the n-photon Fock state. And so, again, we consider detection, we consider monitoring of the environment, and we consider dissipation. In this case, dissipation is modeled simply as a photon that leak from the cavity into the outside world. So we can monitor the environment by simply monitoring these photons leaking from the cavity. And again, I showed that this is the ergotropy as a function of the number of two-level system in the cavity. And again, I showed that the results for photo detection and homodynamic detection of the daemonic ergotropy again outperforms the ideal lossless case in a very broad range of parameters, since here I show again two figure of merits. One is the sort of conversion efficiency, eta, that takes the value 1 when all the variable energy is converted into extractable work, and the value 0 if no advantage is present. And also I show again the ratio between the daemonic ergotropy and the Bayer ergotropy as a function of the two parameters of the model, which are the lambda, which is the coupling between the two level systems and the cavity, and kappa, which is the strength of dissipation. And again, we can see that the daemonic efficiency is great for a very broad range of parameters, but also this daemonic gain is, so the red region is actually the region where dissipation and continuous monitoring outperforms the lossless case. Is actually the plot is red for a very broad range of parameters, so indicating again that this phenomena is quite robust in the parameter space. So we have, as I said, an ergotropy enhancement, both with homodiene detection and photo detection. And also this enhancement is quite robust since before I show the result for the resonant cavity and two-level system. So the cavity, the frequency of the cavity was the same as the energy scale of the two-level system. But in this plot, I show that the daemonic gain, which are these red and blue points, are quite robust against the tuning, but also are quite robust against the detection efficiency. So before I show the results for unital detection efficiency, so perfect detectors, but also with mainly in the case of homodiene detection, we show that in this red points show that the ergotropy gain is quite robust against also the detection efficiency. So it's quite a robust feature of the system. And yeah, this is sort of take-home message. So quantum batteries are a new field of quantum technologies, and I show that correlation are bad. Correlation between the charger and batteries are bad for work extraction, and continuous measurement and dissipation can be used as a resource in this case. And I show this with 3 different setups with increasing difficulties. And yeah, that's basically it. I totally have some outlooks that are in the future. We would like to consider maybe the effect of non-local measurements on the system, and we would like to maybe pursue some experimental implementation of this type of dynamics in quantum platforms. And also we would like to consider more complex type of environments, maybe non-Markovian environments and feedback scenarios. And that's basically it. So thank you for the attention. And if there are questions, I'm happy to answer.
Okay. Thank you, Gabriele. So let's see if there are any questions. Okay, meanwhile, questions are coming. I have one. So, since I am very ignorant in these things and in general in quantum things, so is there something analogous to the Jarzynski theorem in quantum mechanics?
Actually, I'm not very aware of Jarzynski theorem. There are a lot. I mean, Jarzynski made a lot of things, so I don't know if
Jarzynski theorem is something which relates the average of the work that you can extract, actually the exponential of the work with the free energy variation in the process.
That's a very good question, and I don't know actually. Maybe, but I don't know. Because here, I don't know, because with quantum batteries, as I said, we are talking about unitary extraction of work with unitary operation. So I don't know if this can be related to this. I don't know.
Okay, because in the classical case, this is something which provides at least a piece of answer to the questions that you have, but maybe in quantum it's I don't know.
Maybe.
It happens.
Yeah, never thought about that. Definitely, it would be nice to think about that. Yes. Thanks.
Any other question? Okay, I don't see any. So if there are no more questions, let's thank the speakers again, and thank you everyone for being here. I wanted to remind you the next, but I can't find it. Oh, here it is. So the next young seminar will be in July, on day 9, on the 9th of July.